Alrighty, so let's begin. You should have a highlighter or a pencil or something other to make any notes on the side or what have you. Shouldn't take too long here. So just some final thoughts on friction. Here we go. Friction. Even when a single force is applied to an object, it is usually not the only force affecting the motion. That is because of friction. Friction is a force that always acts in the direction of opposed motion. We've talked about that already. I'm reminding you of it. Friction always opposes motion. Does there have to be motion for there to be friction? There does not. It is due in large part to irregularities in the two surfaces in contact. Even very smooth surfaces are bumpy when viewed with a microscope. When an object slides against one another, it must either rise over the irregular bumps or else scrape them off. Either way requires a force. So again, they're talking about how surfaces are not perfectly smooth, and they have to be either, you have to go up and over them, or you have to scrape them off, like sandpaper. The force of friction between two surfaces depends on the kinds of materials and how much they are pressed together. That is the only thing. Notice that it doesn't say anything about area. Rubber on concrete, for example, produces more friction than steel on steel. That's why concrete road dividers are replacing steel rails. Now, you guys are so young, you've probably never seen roadways like that. Have you ever seen one like that? Where it's like a steel, you don't see them too often. They're mainly really only on gravel roads, on bridges. That's where you see them, right? You used to see them all the time. If you're going around Portage there or the perimeter of Winnipeg, you see the concrete divider in between either side, right? And when I was a kid, you would see these kind of things. Why are these ones better? Well, notice the concrete divider is wider at the bottom, so the tire of a side-swiping car rather than the steel body makes contact with it. So much more friction here, which does what? Slows it down. Okay, when you've got a car rubbing up against something like this, not near enough friction. It doesn't really do much. When there is friction, an object may move at a constant velocity while a force applied to it. Please make a note of that. Right? There could be constant velocity. In this case, the friction force just balances the applied force. We keep coming back to these things. The net force is 0, so there is no acceleration. Did I skip ahead or something? Oh, you know what? I remember this, that this handout needs some work. I apologize. I missed an entire paragraph, haven't I? Okay, so on your handout, let's go back to paragraph number 3. Can you find paragraph number 3 on your handout? It says, friction is not restricted to solids sliding over one another. Friction occurs also in liquids and gases, which are called fluids. Fluid friction occurs when an object moving through a fluid pushes back inside some of the fluid. Have you ever tried running a 100-meter dash through waist-deep water? The friction of liquids is appreciable, even at low speeds. If you ever walk through a pool, you know that there's significant friction, which is why these swimmers shave their arms, shave their legs, wear those wetsuits to reduce friction in the water as much as possible. You should listen today, Renee. You don't notice it when walking or jogging, but you'll notice it for higher speeds as in skiing, downhill, or skydiving. Okay, then back to the screen there, right? 4th paragraph. When there is friction, an object may move at a constant velocity while a force applied to it. In this case, the friction force just balances the applied force. The net force is 0, so there is no acceleration. For example, in figure 4.9, the crate will move at a constant velocity when it's pushed just hard enough to balance the friction. The sack will fall at a constant velocity when the air resistance balances its weight. And what's that called? Terminal velocity. I'm reminding you of that. Terminal velocity occurs when the weight force is completely balanced by the air resistance. And the net force is? 0. Okay, if these are balanced here, if the net force is 0, then it's moving at a constant speed. Why don't we call it terminal velocity when something's moving sideways? That velocity, could it get faster? Sure, just push harder. How come the one on the right can't push harder? Because it's falling and gravity's got an upper limit. It's 9.8 newtons per kilogram. Sorry. There's a little question on the side there in a dark box. You got to turn your paper sideways. I probably have it as a clicker. Do I have it as a clicker? I do. Should we clicker these? Come get a clicker if you want. So, question number 1 is, I think I've started. I should have pressed start on this assessment, shouldn't I? Figure 4.6 shows only 2 forces acting in the book. Brayden, time to put it away. Time to listen to me. You've had plenty of time. Figure 4.6 shows only 2 forces acting on the book, its weight and the support force. Doesn't the force of friction act as well? Yes or no? Is there a force of friction here? Yes or no? By the way, you guys had a chance to read that while I was out of the room, so you probably should have formed an opinion already. Yes or no? I don't know. How about you worry about the physics, Josh, and not the grammar? Because I see your name hasn't. Doesn't the force of friction act as well? Is the force of friction acting? No. Why is there no friction? No. Not unless the book tends to slide or does slide or is trying to slide. For example, if it's pushed toward the left by another force, then friction between the book and the table will act toward the right. Friction forces occur only when objects tend to slide or is sliding, or they are trying to move. Now, if I were to put the book on a table that had a slight little incline, would there be friction acting? Yes, how come? Because gravity's trying to make it slide down the ramp. But it's not. It's sitting flat. So the correct answer is no. Number 2. Suppose a high-flying jumbo jet. Hannah, put it away! Seriously, you guys. You guys can't go for 10 seconds without checking. Put them away. Next one is going in here. Put them away. Off. Don't get distracted. Listen to me. Suppose a high-flying jumbo jet cruises at a constant velocity when the thrust of its engines is a constant 80,000 mn. What do you think mn stands for? Meganewtons. Meganewtons. Like megabytes, right?
I can't go to the next question.
What is the acceleration of the jet?
You can't answer.
You can now.
Oh. Okay.
What is the acceleration of the jet? 80,000? 0, 9.8, or you can't figure it out given what I've told you. So what then is the force of air resistance on the jet in the previous question? What is the FF? No one's got eyes that good, I don't think. Come on. This is easy too.
Yes, that's fine. No, I don't know.
Come on, Josh.
I'm blocking the
Please tell me you all got it right.
Oh, God.
Why would you say that the air resistance is 0? The applied force is 80,000 meganewtons, right? The applied force is that. If it's moving at a constant velocity, then that means that the friction force is 80,000. Come on, you guys, think. Okay. Flip. No, there's more. Flip the page over. Okay. Now this isn't in the curriculum, but it's kind of fun and means I can show you the video. So bear with me. Applying force and pressure. Plus, there's some misconceptions that I want to take care of here. So it says you can put a book on a table, and no matter how you place it, on its back, upright, or even balancing it on a single corner, it will. The force of the book on the table is the same. This can be checked by doing this on a basket scale, where you'll read the same weight in all cases. Balance the book different ways in the palm of your hand. Although the force will be the same, you'll notice differences in the way the book presses against your palm. This is because the area of contact is different in each case. This force per unit of area is called pressure. Now, have we done any problems with this? Pressure equals force over area? No, we haven't, and no, we're not going to. Okay? But what they're saying is this, right? You put the book like this, it feels different than this, right? There's more pressure here, right? If you get a much smaller object, right, and heavy, right, that's going to apply a lot of pressure, much more so than if it's flat, because of the area. It's the whole walking on thin ice idea. Okay, where force is perpendicular to the surface area. P is the pressure, A is the area against which the force acts. Force, which is measured in newtons, is different from pressure, which is measured in newtons per square meter, which is called a Pascal, which has only been around since 1960. Relatively new in science terms. Many people mistakenly believe that the wider tires of drag racing vehicles produce more friction. Not true. Get that, Alex? Because it might be on the test. Many people mistakenly believe that the wider tires of drag racing vehicles produce more friction, but the larger area reduces only the pressure. The force of friction is independent of the contact area. Wide tires produce less pressure, and narrow tires produce more pressure. The wideness of the tires reduces heating and wear. It's so that they last longer. I'm just going to do this. It has nothing to do with friction. It's so that they last longer. They don't heat up as much. You exert more pressure against the ground when you're standing on one foot than when standing on both feet. This is because your area of contact is less. Stand on one toe like a ballerina, and the pressure is huge. The smaller the area that supports a given force, the greater is the pressure on that surface. You can calculate the pressure you exert on the ground when you're standing. One way is to moisten the bottom of your foot with water and step on a clean sheet of graph paper marked with squares. Count the number of squares contained in your footprint. Divide your weight by this area, and you have the average pressure you exert on the ground while standing still on one foot. How will this pressure compare with the pressure that you stand on 2 feet? Will it be twice as much? 2 feet, X amount of pressure. 1 foot, 2X amount of pressure? Yeah, half the area, right? More or less. A dramatic illustration of pressure is shown in figure 412. The author applies appreciable force when he breaks the cement block with a sledgehammer. Yet his friend, who was sandwiched between 2 beds of sharp nails, is unharmed. This is because much of the force is distributed over the more than 200 nails that make contact with his body. The combined surface area of this many nail points results in a tolerable pressure that does not puncture the skin. Caution! This demonstration is quite dangerous. Do not attempt it on your own. Please do not try this as part of your final assessment. Can we do this instead of the exam instrument? No, the answer is no. Am I going to do it here in class? The answer is no. But I will show you. Oh, I think I already asked that question, didn't I? Yes. I have to pay attention to what's on my screen. Would you like to see a video of that? First, you have to answer this question. In attempting to do the bed of nails demonstration, would it be wise to start with just a few nails and then work your way up to more?
No. Oh. Oh.
Yes or no? Did you think about it?
Yeah.
Because I've given you the answer. Braden, you got to press enter. Yes. Apparently you learned something today. Thank you. You knew that before. Well, that's good. That is definitely good. No, 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 and no. There'd be one less physics teacher if you did that. Oh, now, here's a harder question. Okay, you look at the picture there. You'll see that the gentleman on top, with his shirt on, thankfully, is smashing the cement block, concrete block. Right? So, and it says cement, and that's a concrete block. The massiveness of the concrete block plays an important role in demonstration. What provides more safety? A less massive block, in other words, a smaller one? A more massive block, or a bigger one? Or it doesn't really matter, it's just there for show. Which one provides more safety? Bigger block, sorry, smaller block, bigger block, doesn't really matter. This one you'll have to think about. Why is a bigger block better? Who can tell me? The greater the mass of the block, the smaller the acceleration of the block in the bed and elsewhere in the front. What if you had no block at all? And you just hammered on that flat board with the nails toward the guy. Yeah, ouch! What does the block do? It actually slows the acceleration down, right? Takes the acceleration down. The greater the mass of the block, the smaller is the acceleration of the block, and the bed and nails towards the friend. Much of the force wielded by the hammer goes into moving the block and breaking it. It's important that the block be massive and then a break upon impact. Okay? You wouldn't do it with just a hammer. So why do they do it this way? Well, it wouldn't be very dramatic if they just put the bed and nails on top of the guy and then kind of like with a finger went like that, right? It wouldn't be very dramatic. So the actual block is more important than I think the number of nails. And I'm recording this. Do not attempt on your own.